In the previous video, we had an example of a 1D momentum conservation problem. We investigated the scenario of a kid walking home from school. He was greeted by his pet tiger. The tiger gave him a big hug as he pounced on him, and we used momentum conservation to find their final velocity. In this example problem with two skaters, Alfred and Barbara, we are going to investigate momentum conservation in 2 dimensions. When I write momentum as a vector like this for a 2D momentum problem, momentum is a vector with components. So that means I have a notion of the x component of a momentum vector, and I have the notion of the y component of a momentum vector. If I write momentum equals mass times velocity, well, the x component of momentum will be mass multiplied by the x component of velocity, and the y component of momentum will be mass times the y component of velocity. Mass itself is a scalar quantity. Mass does not have x and y components affiliated with it, but velocity is a vector, and velocity will have an x component and a y component. So in this problem, we have two skaters. One skater is skating to the east, which I'll call the x direction. One skater is skating to the north, which I'll call the y direction. And we are given the masses of the skaters and their initial speeds. So the way I drew this problem, we have the skaters Alfred and Barbara. Presumably they will skate in the same direction. They will collide, and then they will hold on to each other and move off together in some direction, kind of like that. If momentum is going to be conserved, this means that both px total and py total must be the same before and after the collision. I am not really going to be interested in the details of the collision itself. I am only going to be interested in what the system is doing before the collision and after the collision. So to look at this problem, when I write total momentum, when I write P total, I mean the momentum of every particle in my system. In this particular example, I have two particles in my system. Those two particles are my skaters, Alfred and Barbara. So to write the total momentum, I would write total momentum is the momentum of Alfred plus the momentum of Barbara. Now, at this point, I did not yet specify, am I talking about their initial momentum? Am I talking about their final momentum before the collision or after the collision? Well, we know that the total momentum is going to be the same in both cases. Before the collision and after the collision, this will be the same vector. But the individual momentum vectors could change from before the collision to after the collision. As long as the total momentum does not change, that's okay. So when I write total momentum, I mean the total momentum in the x direction will be the momentum of Alfred in the x direction plus the momentum of Barbara in the x direction. And the total momentum in the y direction will be the momentum of Alfred in the y direction plus the momentum of Barbara in the y direction. And both of these will be conserved quantities. These will be two quantities, P total x and P total y. These are both going to be the same before and after the collision. So for this problem, let us first find the total momentum of the skaters before the collision. So to do that, we are not going to worry about the collision which occurs here. We're going to look at Alfred's momentum before he collides. We'll look at Barbara's momentum before she collides. So for the momentum of Alfred, I could say the momentum of Alfred is equal to the mass of Alfred times the velocity of Alfred. Now momentum, as I said, has components. So I could say the momentum of Alfred in the x direction will be the mass of Alfred times the velocity of Alfred in the x direction. If I look at what is given in this problem, we know his mass is 83 kilograms, and we know his speed is 1.7 meters per second, And if I look at the way his velocity was described, he is only moving to the east. So I could phrase this as the x component of his velocity is 1.7, the y component of his velocity is 0. So 83 times 1.7, and if I put that in a calculator, that gives me 141.1. Similarly, I could find the y component of Alfred's momentum. I could write PAY is equal to the mass of Alfred times the y component of Alfred's velocity. So I would write that as 83 for his mass, and because his velocity is entirely to the right, only in the x direction, I would say technically he does have a component of his y velocity. The component of his y velocity is 0. So 83 times 0 gives me 0. I will do the exact same analysis for Barbara's momentum. So I could say the momentum of Barbara in the x direction is going to be the mass of Barbara times the velocity of Barbara in the x direction. Now, Barbara has a mass of 55 kilogram, and she is only moving to the north. So the x component of her velocity is going to be 0. And for her momentum in the y direction, the momentum of Barbara in the y direction, I could write as the mass of Barbara, the y component of Barbara's velocity will be 55. Now I look at the direction that she is moving. She is only moving to the north, so her entire speed is causing her to move to the north at 2.2 meters per second. So I'll write this as 55 times 2.2, and if I put that in a calculator, I get 121. So now I know the x and the y components of each skater's momentum. I could say Alfred's momentum, PAX equals 141.1, PAY equals 0, and I could say Barbara's momentum could be written as PBX equals 0, PBY equals 121. When we did this analysis, we only considered the initial time, the time before the collision. But if I add up the components of the momentum of both skaters, so I could say PAX plus PBX equals 141.1 plus 0. And when I add those, I get 141.1, and PAY plus PBY gives me 0 plus 121, which gives me 121. This is the total momentum in the x direction, and this is the total momentum in the y direction. So I could say that P total in the x direction is 141.1, and P total in the y direction will be 121. These are two separate conserved quantities. I don't know the details of how they're going to collide, but I know that after their collision, they will be moving off in some direction, more or less up and to the right, and their total momentum will be 141.1 in the easterly direction and 121 in the northerly direction. So let's find their final speed now. I could say momentum is equal to mass times velocity, and this is true at all times. Right now, I'm specifically going to be interested about the momentum after they collide. Well, the momentum after they collide will have an x and a y component. So I could say px equals mvx, and I'm going to leave a little space here. Py equals mvy. Well, we know what their momentum is going to be in the x and y direction after they collide. Their momentum in the x is 141.1, and their momentum in the y is 121. Let's think about what else is going on in this problem. Because both skaters cling to each other and move off together, we know they're going to have the same final velocity. So I could think of them as two separate objects with the same final velocity, or if I want, I could think of them as one bigger object with a single final velocity. And that also is a valid way to think about this problem. So the mass of the skaters after they collide, I'm going to treat it as a single object of mass 83 plus 55. So I'll write this as 83 plus 55 Vx, and I'll write this as 83 plus 55 Vy. At this point in the problem, we have enough information. We could find the final x component of the skater's velocity and the final y component of the skater's velocity. And if I put that in a calculator, I find Vx equals 1.02 and Vy is 0.88. So how do we translate velocity to speed? Well, speed is the magnitude of the velocity vector. So what I found here is if I were to draw their final velocity after they collide, here is their final velocity, 1.02 in the horizontal, 0.88 in the vertical. Their final velocity is going to look something like this, where the horizontal component of this vector is 1.02, the vertical component of this vector is 0.88. This is my Vy final. This is my Vx final. And if I want to relate speed to velocity, speed is the magnitude of the velocity vector. So to find the speed, I just have to find the magnitude of this vector. So I will Pythagorean theorem it. So I could say that the final will be equal to the square root of 1.02 squared plus 0.88 squared. And when I put that into a calculator, I find that their final speed is going to be V final equals 1.35 meter per second. In the next part of the problem, we are asked to find what percentage of the kinetic energy of the skaters is lost in the collision. Before we actually go ahead and solve that question, I first want to take a moment to mention, when you encounter a problem like this, be careful about how the problem is phrased. This problem asks you to find the percentage of kinetic energy lost in the collision. But a different problem might ask you to find what percentage of the kinetic energy remains after the collision. And even though it is essentially the exact same problem, the techniques are all the same, technically the question is asking for something different. So just be careful about how a problem is worded. Make sure when you're doing homework that you're answering exactly what the homework asks for. So we have two skaters. Before the collision, which I'll call the initial moment, they are skating with a speed that is given and they have masses that are given. After they collide, we found what their speed was after the collision, and we treated them as a single object because they are moving off together. So I could say before the collision, their total kinetic energy, so I'll call that KE total initial, would have been the sum of their individual kinetic energies. So before the collision, the kinetic energy of Alfred initial plus the kinetic energy of Barbara initial. Now, kinetic energy is 1/2 mv squared, and we are looking at kinetic energy before the collision, so I'm going to use these speeds from before the collision and their individual masses. So I could write the total initial kinetic energy as 1/2 times Alfred's mass, 83, times Alfred's initial speed, 1.7 squared, plus 1/2 times Barbara's mass, 55, times Barbara's speed squared before the collision, and that would be 2.2 squared. If I put these numbers into a calculator, I find the total initial kinetic energy is 253 joules. Now let's find what is the final kinetic energy of the skaters after the collision. There are two different ways I could think about this question, but they are fundamentally equivalent. They're both really the same way of thinking about it. One way I could think about it is treating the two skaters as a single, more massive object. So I could say the KE total final after the collision, I could write that as 1/2 mv squared. I am treating the skaters as a single object of mass 138 kilograms. So I would have 1/2 times the mass, 138, times their final speed squared, 1.35 squared. And if I put those numbers in a calculator, I find that their final kinetic energy is going to be 125 joules. A separate way that I could have thought about these skaters is I could treat them as separate objects. We will find the exact same result though. Because I have two skaters, I will treat their masses individually, but we do know they will have the exact same final speed. So I would write that as 1/2 times 83 times 1.35 squared for Alfred, plus 1/2 times 55 times 1.35 for Barbara's final speed squared. But if I put that numbers in a calculator, I still find the same 125. So we don't really get any different result at the end of the day. Now let's think about what the question is really asking for. What percentage of the initial kinetic energy was lost? So first I'll ask how much kinetic energy was lost. Well, before the collision we had this much kinetic energy. After the collision we had this much kinetic energy. So how much kinetic energy was lost? I could say 253 minus 125. That gives me 128. So this is the kinetic energy that's lost in the collision. Okay, what percentage of the kinetic energy was lost? That is essentially asking what percentage of 253 is 128. I could write 128 divided by 253. When I put that in a calculator, I find 0.506. So if I multiply this decimal number by 100%, that essentially tells me that 50.6% of the initial kinetic energy was lost.